Good morning. Welcome back to Classical Mechanics 1. This is the 10th meeting, 26th October 2021. Let me just make sure you can hear me. Am I audible?
Yes, sir. Good morning.
Okay, thank you. All right, while we wait for the rest of the participants to come, let me just remind you that there's a homework due this week, Friday. Please ensure you hit the submit button and submit on time. Today, I intend to return to our discussion of Newton's laws and Galilean principle of Galilean relativity. Go over some of that. Last time I had overlooked to make the distinction between external forces and interparticle forces when discussing Galilean principle of relativity. And so I want to go over that and clarify some things over there and correct some things from last time at the very end of last lecture. Okay, are there any questions while we wait for a few more to join us?
Hello, sir. This is Ayan. In question number 1 of problem set 4, I think we need the additional constraint that x and y are orthogonal. Otherwise, simply x cross y is equal to z does not imply that they must be mutually orthogonal.
Okay, let me look at the phrasing of my question. Do I have something wrong? Wait a minute. Well, okay. First of all, I think in this question, we don't say anything about orthogonality per se. Or okay, wait a minute. Okay, perhaps I have overlooked to say that x, y, z are orthogonal unit vectors. Is that what you're pointing out?
Yes, sir.
Okay.
No, actually, I think it's fine because the fact that the unit vector, the fact that the unit vectors does imply the orthogonality.
No. I think you can take x and y on just some random vectors on the xy plane and define z by x cross y. So it will not work, I think.
Yeah, even for this, I had to assume that, it was an orthonormal set. Like I even mentioned that I assumed that fact in the question.
Yeah. I think so. I think I have overlooked to mention that it is written in the title, but not in the question.
Sir, I just have like one thing. If they weren't, if x and y weren't perpendicular to each other, then z wouldn't be a unit vector. So the fact that z is a unit vector implies that they're orthogonal.
Okay.
Yeah. So I think it is fine. Yeah.
Okay. So yeah. Okay. You may let me off the hook. Okay. Yeah, there is something to what both are saying. Yeah. So. All right. So just to be clear, the first question came from Ayan Nath. Am I right?
Yes, sir.
Yeah. Okay. So while I was looking at the question, somebody else has answered. I didn't catch the name. Who spoke? Mentioning that the unit vector condition.
Sir, Sankalp.
Sankalp. Yeah. So I do believe, yes. If x and y were not orthogonal, then their cross product, and they are already told, we are told they are unit vectors, then their cross product would not be a unit vector otherwise. Is that make sense, Ayan?
Yes, yes, I get it now. Thank you.
Okay, great. Yeah. So yeah, but no, I do admit that I should probably have mentioned it in the question just to make things doubly clear. But I have been let off the hook because the question, I think, is still correct. Okay. Any other question?
Yes, sir. Like, I mean, yeah, what does Newton's equation of motion mean? Like, is it the differential equation we get by F equal to ma, or is this the solution of this differential equation?
Okay, the Newton's equation of motion, by that we mean this equation of motion, this differential equation, not its solution. Then we would say the solution to the equation of motion.
Yes, sir. Thank you, sir. And one more question I had.
Yes, Ruptak. Yeah.
So like, so it's like I mean, like the system of a point being on a sphere, like this is this has degrees of freedom. I mean, 2 degrees of freedom. Right. So it's like now, if we just take I mean, like Cartesian coordinates for like a point on the sphere, then
okay. Wait. Let me just interrupt you here. So this concerns the problem from the assignment. Am I right?
Yes. It's
okay. So I hesitate. I mean, while I welcome your discussion of it, this problem has not yet been submitted by most of you. So I hesitate to discuss it unless there is some clarification or even for you to suggest answers. If you have a question about the phrasing of the problem, please do ask that. But let us be aware that this problem set has not yet been submitted.
Yes, sir. I actually had a like clarification for like the I mean like the whole system.
Okay.
It's like now it's like if we just take I mean like take the Cartesian coordinates of a point, I mean like on the sphere, then the z component depends on x and y.
Yes.
But it's not fully dependent because it's like there are for each x comma y there are 2 possible z, like one above and one below the like, so can we tell that like this z is like fully dependent on x y, like
no, okay. The point is that see, the sphere is a nice, interesting space, and if we want to set up coordinates on the sphere, unfortunately, a single coordinate system will not suffice. We need a minimum of 2 coordinate systems, and that is what you're getting to. Yeah. So you, in more technical language, you need 2 patches or 2 coordinate systems to cover the sphere. And that corresponds to the 2 possible values of z that you pointed out, given x and y. So there's nothing wrong with that. Some spaces require several patches to cover them with the coordinate systems, and the sphere is a prime example of that.
Yes, sir, but like the thing is that like this has like then it I mean like 2 parameters isn't like sufficient to define each point on a sphere. So that's
correct. Yeah, no, 2 parameters are sufficient. You may need an additional yes or no condition. That is not a free parameter. You can say z positive, z negative, right? So that doesn't count as a free parameter, real parameter. It counts as a discrete variable.
Yes, sir. Thank you, sir.
Yeah, you're welcome. Yeah, so it labels patches. This additional discrete variables labels which patch you're on. Northern hemisphere patch, southern hemisphere patch. You decide.
Oh, sir, I didn't understand. You said
okay. Now, see the sphere, this globe. The way I've done it, you can use coordinates x, y, and z to specify a point on the sphere. So, I mean, in the usual way, upwards is z and x and y on the plane. Okay, so now for given x and y on this plane, there are 2 points on the sphere that correspond to a given pair of x comma y, namely z on the upper hemisphere and z on the southern hemisphere. This is what was pointed out. So I forget who, Ruptak Masumdar mentions that it is not if you have to specify x and y to locate a point on the sphere, you need to say what z is also. Now, in answer to that, I said that it's not allowed to be a free real parameter. X and Y are freely varying. It can be any point in this equatorial plane. But Z can take only two values, and it is enough if you say Z is above or Z is below. That's enough. It's not a free real parameter anymore. So in that sense, you really need only two real parameters to locate a point on a sphere. Does that clarify?
Yes, sir. Yes, sir.
Okay, good. And I further commented that the choice of this Z up and Z down, or northern hemisphere, southern hemisphere, is a way of labeling different patches or coordinate systems that are needed to cover the sphere. A single coordinate system doesn't suffice. Okay. Any other question?
So just to clarify this last point,
Yes.
by a single coordinate system, you mean a single coordinate system defined like this in terms of X, Y, and this other coordinate? Because
in terms of X, Y, that's it. Only X and Y. Yeah.
Sorry, right.
Yeah.
Okay.
Yes. The two patches. Yes. In this very sense. Yeah.
Okay, but
Yeah.
there could be other coordinate systems which do not need this extra. Discrete parameter.
No. I claim that for the sphere, you really need minimum of two. You can choose three. See, the point is that you think of a sphere and you think of covering the sphere with kerchiefs. Yeah. Question is, can you manage with one kerchief and have it specify the points of the sphere in a one-to-one manner? Yeah. And the answer is no. You need at least two kerchiefs.
Okay, maybe I'll think about this and ask again later.
Okay, sure. Yeah.
Sir, I have one clarification in the same question about the sphere thing. Like usually what we do is while defining degrees of freedom, we have 1 degree, like 3 degrees of freedom to specify the coordinates of the center of the sphere, right?
Okay. And wait. Let me be very clear. This is the surface of a sphere, not a solid sphere.
Yeah.
And,
so
and it is a fixed sphere. It is not allowed to move. The sphere
okay, that's what I wanted to ask. Yeah.
Okay.
That's what I wanted to ask. If it was a fixed sphere or was it movable?
Okay, it is a fixed sphere. I am sorry. I should have said a fixed sphere in the question. Yeah. Okay, you are right. I should have said a fixed sphere, not a moving sphere.
Sir, if we use the phi and theta thing for the polar coordinates, then we can cover the sphere in just one.
Nearly, but there are places where this breaks down. This is the problem. There are certain places where there is not a one-to-one correspondence between points in the sphere and theta and phi. Let us recall, for instance, at the North Pole, the azimuthal angle phi can take any value. All those values correspond to the North Pole when theta is equal to 0. Does that sound familiar to you?
Oh, yeah.
Okay. So in that sense, it doesn't provide a one-to-one correspondence between points in the sphere and theta phi points in the theta phi plane.
Okay, sir.
Yes, that was Rishabh Sharma. Yes. Okay. Any more questions? Yeah. So in this problem concerning the point particle moving on a fixed sphere, when I ask you to give suggest possible physical quantities, I would ideally like you to specify some coordinates. I mean, that would be an ideal way to proceed rather than a general statement. It's okay if the coordinates don't cover the whole sphere. That is a nicety that we are not going to be worrying about much. But please do try to suggest some variables, not just words. Okay. Yeah. Any other questions? Okay. If not, let me now go back to our discussion of Galileo's principle of relativity. As I said at the beginning of this lecture, I wish to go over it once again, in part because there are things I didn't say last time, in particular concerning external forces external to the frame, external to the ship, and interparticle forces within the ship in Galileo's discussion. And that distinction is very important. And by not mentioning it, I misspoke, and I want to correct that at the very end of last lecture. So I will do that right now. Okay, so let me share my screen. Yeah. Okay. All right. So now let us, I mean, Galileo's relativity principle is a very important concept in physics, and that is why I spend a little bit more time on it. So let us recall things from last time. A little bit of repetition will be there. Yeah. So notice that Newton's second law, when I say Newton's second law, I mean Newton's second law equation, namely mr double dot is equal to force, yeah, relates the force to the second derivative of position along a trajectory, as opposed to the first, third, or other derivative of the particle's position. And I said that this was to incorporate Galileo's relativity principle, which says roughly that there is no dynamical way, and I will clarify this, no dynamical way of telling if a frame is at rest or moving uniformly relative to an inertial frame. So to make this a little clearer, let us make things a bit more concrete and go back to what Galileo discussed in 1632. So this appeared in his book concerning a dialogue between the two principal world sciences or some such thing. I forget the title of his famous work. It was a book where he discussed, he presented a discussion between the Ptolemaic and Copernican viewpoints on celestial mechanics, in particular the geocentric and heliocentric models. And in the course of that discussion, he brought up this idea of Galileo's relativity principle. Yeah, so it is a landmark development, this book of his. He presents it in some sort of third person. Somebody called Salviati or something is discussing these things, yeah, yeah. I think you are aware that the earlier worldview was a geocentric one, which was endorsed by the church authorities as well, and it was somewhat heretical to go against that. And then there was the Copernican, view where that the Earth perhaps went around the sun. Yeah. Now and so he presents some discussion of these two viewpoints and a debate, and it is fairly clear from that that he's suggesting that the Copernican viewpoint is preferable. But he's very careful about how he presents the discussion. He was, I believe, given to believe that if he presents it in such a way that he says that the heliocentric view is a model for convenient discussion of celestial phenomena, basically that, and not that the Earth is not the center of the universe, then it would be acceptable. He was under that impression, I believe, but unfortunately that was not quite accepted, and he was taken to task for suggesting this, even though he was very careful in the writing, and he eventually had to pay with his life for that. Now there is an irony in this whole thing, because Galileo's principle of relativity finally says that it is equally valid to think in terms of the frame of reference of the sun as it is through the frame of reference of the Earth. Yeah, so his own principle in a sense makes it meaningless to talk about a heliocentric view being better than a geocentric view. But one must also admit that there are advantages to a heliocentric view in practical calculations or organization of data, simply because the sun is very heavy. The center of mass of the system really does lie very close to the sun center. So there are advantages to that viewpoint, but Galileo's own principle makes it meaningless to talk about one frame being better than the other in a strict sense. So the whole thing is somewhat ironic. But leaving aside that aspect, let me now come back to Galileo's relativity principle. So in 1632, Galileo observed that it was not possible to detect the uniform motion. When I say uniform motion, I mean constant velocity motion without rocking, without shaking, of a ship relative to the shore by performing mechanical experiments under the deck of the ship. And the reason he says under the deck of the ship is because he doesn't want you to look out of the ship or concern yourself with any external influences. You're only allowed to do experiments with particles and bodies inside the ship. In fact, he describes the procedure. He says you take with you a bottle with water and a big bowl, and you take some fish in the bowl, and also you carry some butterflies or some flies with you. Take them all and keep them in this room under the deck of the ship. And then the ship is either parked in the dock or it is moving uniformly in the sea. And then you can do experiments inside the ship. And the experiments are things like watching the water drop from the bottle to the bowl. You watch how it drops. I mean, does it come down in what direction, how fast, such questions. You're also allowed to throw a ball to somebody else in the same room, or to throw it against a wall and see how long it takes to hit the wall. Yeah, you're allowed to watch the flies, how they fly. I mean, do they have some preferred direction in which they generally fly? You're allowed to observe such things. And he also observes the fish, how they fly, how they swim in the water. And he does all of this on the one hand in a ship that is at rest in the dock, and one that is moving uniformly. And he asserts that it is not possible through such experiments to tell whether the ship is at rest in the dock or moving uniformly. So this was Galileo's very detailed and picturesque discussion. So just to summarize, these experiments that you could conduct could include observing the motion of projectiles. Yeah, I mentioned things like how long it takes for a ball that is thrown horizontally, say, at a given speed to reach a wall within that room. The manner in which water drips from a jug, how flies fly, how fish move, and so on. Okay, so these were the types of experiments he envisaged. Yeah, and I will make clear also what kind of experiments he did not permit, because that is equally important. And that is the next point. It is important to note that Galileo's principle is not concerned with forces external to that little lab room inside the ship. So he is not concerned with forces outside. In particular, let me take a specific example. If the acceleration due to gravity, which is an external force, it is not something between particles within the ship, within the room in the ship. In particular, if the acceleration due to gravity varies with location, and that is true, it does vary a little bit with location on the Earth's surface, and it certainly varies with height, then it may be possible for an observer in the uniformly moving ship to infer that the ship's frame is moving relative to the shore. Yeah, simply because the acceleration to gravity would change, and then you would say, oh no, this is not a ship that's at rest. Yeah, so Galileo is forbidding you from doing such experiments. You're only allowed to do experiments between particles within that ship, Of course, there is gravity, you cannot prevent that, but then you have to work within the approximation where the gravity doesn't vary with location. Yeah, so that assumption is in here. So Galileo's principle, a little bit more carefully stated, asserts that the relative motion of bodies in the lab, is the same whether observed when the ship is docked or when it is uniformly moving. Okay, so I was not sufficiently explicit and careful in saying some of these things, which I really should have last time at the very end. Okay, so this idea is elevated to the principle of Galilean relativity, which states that the laws of mechanics must take the same form in two inertial frames that are in uniform motion relative to each other. Okay, so this is we will make it more explicit. We will give a mathematical expression for what we mean by this as well. Yeah, or in other words, the Newton's laws hold in one inertial frame, if and only if they hold in another inertial frame. So that is another way of thinking of it. I will elaborate on this shortly.
Sir?
Yes,
So is it experimentally possible to prove the Galilean principle of relativity?
Yes, one can check it. Yeah, precisely by the experiments I described. You take your friend, go inside this room in the ship. You throw the ball to your friend at a certain speed, at a certain angle, and ask what is the trajectory of that ball. You plot it and measure how long it takes for your friend to catch the ball. You repeat that same experiment in a ship that's moving. Yeah. Now, no matter whether the ship is moving in the direction in which you throw the ball, opposite to the direction you throw the ball, perpendicular to the direction, no matter what way the ship is moving, it will take exactly the same time. Or, I mean, this is to be checked by doing experiment. It takes exactly the same time for that ball to reach your friend. So, indeed, this can be checked.
But the ship will sink in while moving in the water.
No, that is what I said. We have to, okay, see, we have said that we are ignoring the rocking motion. That is, we are assuming that the ship is moving uniformly. Yes, this is an idealization. And so you have to choose a day when there is very little wind and the sea is not very turbulent. And yeah, so you have to minimize all those other effects if you want to check this principle.
Isn't the initial reference frame concept came after Newton?
Sorry, could Vijay
Yes, haven't the initial reference frame concept came after Newton? So, how did Galileo say about initial reference frame?
No, I'm not hearing you very clearly. You said something came after Newton. The inertial concept?
Yes, inertial reference frame, and the concept came after Newton, didn't it?
No, see, the name we give to it, inertial, is of course, and the idea of free particles traveling in a straight line is something that comes somewhat later. But so let's be very clear. Galileo is saying something very concrete. What I am saying here is a refined or elevated principle, which we now call Galilean relativity principle. Galileo was saying something very concrete. You take a ship, you put it in water, you move it fast, you move it slow, you move it uniformly, or you keep it at rest. You do experiments inside, compare them. That's all Galileo is suggesting.
Okay.
Yeah. Yes.
So while performing experiments, first we perform on the shore of the sea, while the ship is in rest, and then we perform while in the sea.
Yeah.
So if there comes small error, how do we know that this error comes because the ship was shaking, or this error is because due to that Galilean principle is false?
Correct. Very good question. I mean, this question applies to any experiment. There are many reasons why the results of an experiment may not match your hypothesis, and the onus is then on the experimenter to reduce those effects, so and convince themselves and others that the effect is not because of the rocking of the ship or of the wind and other such effects, and not a violation of Galilean relativity. So yes, you point out a very good point. It is up to the experimenter to establish to your satisfaction that the violation is not due to other effects or external forces. Yeah, there is. Your point is well taken, but you need to minimize those. As you do it once, then you try to reduce it further. You just wait for a day when it's somewhat less windy. Yeah, so you need to try to reduce those effects.
So like one day we do it when the winds are fast, and one day when we do it the winds are low and the error reduced, then we can confirm that the errors were due to the technical errors.
Correct.
Not because
roughly. See, I wouldn't say you can ever confirm, but you can provide evidence in favor of the Galilean relativity principle. That is as much as you can do in science. You can never confirm a principle in science. You can only falsify it, or you can provide evidence in favor of it. That is about all we can do. And by the way, even if the ship is rocking, suppose you throw the ball very, very fast, so that those effects can be neglected to your accuracy. Yeah, so it's possible to in relative terms reduce certain other effects. Yeah, I mean, it is true there are always some earthquakes going on and there is some seismic events going on, but it may be possible to make the effect you wish to see very strong so that those effects become subleading. Yeah, so yeah, one has to be very clever about this. Yeah, is that okay?
Yes, yeah.
Okay, fine. Yeah. Okay, so returning to our discussion. Okay, this was just a parenthetical remark.
So,
okay, Ripunjay has a question.
So,
but there is some audio problem from Ripunjay.
So now am I audible?
Yes.
Yes, sir. I wanted to ask, what does Galileo say about acceleration? Does he say that we can't detect acceleration, or he says that we are not talking about acceleration? What is his take in this aspect?
No, Galileo is not talking about acceleration. Galileo is only talking about a ship that's moving uniformly. And Galileo, I mean, or Newton, Galileo, everybody, they finally conclude that acceleration is detectable. It is not as though it is undetectable.
Yes, so basically the reason that I'm asking this is, let us say that we have something where we have acceleration which can, let us assume that acceleration cannot be detected. Then our laws of motion, they need to take that into account. So it has to be higher than second degree. So if Galilean principle says that we can't detect velocity, then the law has to be second degree, right? Or more.
A minimum of second degree. Yeah, 2 or more.
Yes, sir.
You're right.
But if we can show that even acceleration cannot be detected, then it becomes the second degree equation. Because if we have a higher degree an equation, it will imply that acceleration can't be detected, but we can detect acceleration. So this credit goes to Newton for saying that no, acceleration can be detected, or it goes back to Galileo. Because if Galileo knows this, then Galileo also has the second law, right? And then the third law.
Okay, now, the question of attribution is not one that I can entirely resolve over here. I'm not 100% sure what Galileo says about acceleration. I do believe he had at least some understanding of these things, but it did take time before things could be formulated really precisely.
So because this is in a way like showing that yes, it has to be second degree. It eliminates the doubt of it being third, fourth, fifth, whatever it is, because acceleration can be detected. So it must be a second degree equation, right? If anything can be detected, it must be that degree only.
Sure.
So in that aspect, this solves the problem of why second degree.
Sure. Yeah. So yes, you would have to do experiments to show that the acceleration is detectable, and then there's something to what you say. Yeah, but I wish to hold off on discussion of accelerated frames till a little bit later. But your point is well taken, that you could try to eliminate higher order in time differential equations by the sort of procedure you mentioned. Yeah. Okay. Okay. Is that all right, Ripunjay?
Yes, sir. Yes, sir.
Yeah, your point is well taken. Yes. Now, Galileo's principle of relativity, as I said last time, continues to hold in special relativity. That is when speeds of objects or relative speeds between frames approaches that of light. And to accommodate the constant series of the speed of light, Einstein modified the transformation rule that relates coordinates in two frames of reference that are in uniform motion relative to each other. He did not tamper with Galileo's principle of relativity. It was retained. Yeah. So just to recapitulate from last time, in Galilean relativity, one makes a couple of some additional assumptions. One is that the mass of a particle is the same in two frames that are in uniform relative motion. So that is one very basic assumption. And also that both observers in these two frames use the same scale for measuring distances and agree on time intervals between any pair of events. So I did mention these last time, so let me not belabor that. Yeah. So in other words, uniformly moving measuring sticks have the same length as when they are observed at rest. And a clock that is moving at a constant velocity neither slows down nor speeds up relative to a clock that is at rest. Now, with these assumptions, we can motivate the appearance of acceleration r double dot rather than velocity r dot in Newton's second law. So this is, I mean, we have been discussing this, so it's not going to come as a surprise to you, hopefully, but I just want to do it a bit once again. It ensures that when referred to a frame S prime moving at constant velocity u relative to an inertial frame S, Newton's law takes exactly the same form for a system of particles which may be interacting with each other. So let me give some examples to clarify this. So here is our frame S. Yeah.
Excuse me, sir.
Yes, Shubham Kumar. Yes.
Sir, I had a doubt regarding the last question which Ripunjay asked.
Yes.
Like, why couldn't we have like two terms in? How could we eliminate the higher derivatives? I mean, we could have.
Okay, there could be some cancellation and so on. Yeah.
So we could have terms with second derivatives and another term with higher derivatives. I mean, that could also be.
Sure. Yeah. See, I am not. No, his point was that perhaps you can use the detectability of acceleration to somehow constrain the equation of motion. And I think that is a reasonable suggestion. In detail, how you do that, one had to be a little careful.
No, sir. I mean, I was talking about that only. Yes. I mean, he said that because acceleration is detectable, we could eliminate higher order derivatives. But like, we could have a second in the equation of force. I mean, we could have a second derivative, which like so that we can detect acceleration, and we also had we could also have terms with higher derivatives in addition to that.
Okay.
Sir, can I answer this? Can I attempt to explain what I'm thinking?
Okay, please. Fine. Yeah. Okay.
So my idea for this is like, so the reason that we are able to do this is because the fundamental reasoning, the source or the origin of force, we are assuming it to be a physical constant, right? So the effect is basically r d2r by dt square. Now if we substitute r plus vt, say r plus vt, that is r prime, then first derivative will eliminate time, second derivative will eliminate v, and we have the same thing. Now if we have acceleration, that is going to be second order in time, it will be r plus half a t square. And if we have higher terms, then we can't eliminate A, right? Because when we take the first derivative, first time will go, second time will go. For higher derivatives, we'll have some constant which will come in addition with R by D2R or DNR by DTN plus some number. So we don't need it. So even if we have a term in higher degree, that thing will come, because when we make a transformation, that thing can be detected. So it won't match with our observation, right?
Okay. See, I think, okay, I hesitate to, okay. I think I kind of follow what you're saying, and that higher derivatives would be disallowed. Is that what you're saying? Would be disallowed if
yes, sir, because frame transformations will lead to detection.
If the acceleration is detectable. Okay, yeah. So okay, see, I'm sympathetic to your view, but without actually doing this carefully, I'm a little hesitant to take it on faith. See, because it's one thing to say that something can't be detected and thereby eliminate a certain term. Now, when you say something is detectable, then things get a little bit more complicated. I am willing to go along with you as that is a possibility, but
yes, I was also like
some cancellations among these higher order terms to somehow conspire to do something. I'm just putting a word of caution here. I have not thought about this carefully enough to be sure.
So yes, sir, like I was talking about that only. Like if the equation is m r double dot plus some constant k into r triple dot, this could also like this has the higher derivative term, and here also acceleration is detectable. So like what Ripunja said, that all higher ordered terms will be eliminated, that idea I was not really convinced by. That I was like pointing out.
Okay.
So in that case, we don't need a second derivative. That is what my point is, because triple dot will take care of second dot, like r double dot, in a way. It's like we don't have to define velocity for our, like in our frame, we don't need to add velocity because we want to deal in second order, right?
Okay. So I think this is an interesting discussion, but I hesitate to devote more to this without more careful thought as to what is being done. So if I think both of you have a point, I haven't thought about this carefully enough to give a conclusive answer to this question. Please bear with me for that. What I would like to do right now is to try to motivate the existing. Galileo is not saying anything about accelerating ships. That much is clear, at least in his Principle of Relativity. I mean. So insofar as that is concerned, let us try to restrict ourselves to the Galilean principle and see how it motivates Newton's second law. You are right, there is more to this story if you want to argue why higher derivatives are not present. And in some sense, it finally comes down to checking the consequences of the law for observed phenomena. And if it is in reasonable agreement, that will eliminate higher order derivatives. And I think in some way, what you're saying reduces to that. Okay, just a second. So sorry, Ripunjay and Shubham, I am not able to take this particular discussion in a very fruitful manner right now. So I hope you will excuse me for that. And let us return to the Galilean principle. I think this is already evident to you, but let me just go over it. So for example, suppose the frames coincide at t equal to 0. So that was what this picture shows. The frame S prime is moving in this direction with velocity u. The frames coincide at t equal to 0, and the position vector of a particle is r with respect to s and r prime with respect to s prime. And the two vectors are related by the formula r prime is equal to r minus ut. Yeah, so and ut is the position vector of the origin of s prime relative to s. So given this relation between r prime and r, we notice that r dot or r prime dot is equal to r dot minus u, and therefore r prime double dot is equal to r double dot. Okay, so the two accelerations are equal in the two frames. Yeah, r prime double dot and r double dot are one and the same. And therefore, to begin with, the equation for a free particle is the same in both frames, namely mr double dot equal to 0 and mr prime double dot equal to 0. So the two equations are the same. If it was a free particle in one frame, it is free in the other frame. In other words, a particle is free in one frame if and only if it is free in the other. Okay, so this is the sense in which the equation of motion for a free particle takes the same form, identical form in both frames, which are in uniform relative motion. Yeah, so Newton's second law is able to account for that at least. Let us take one further step and look at Newton's second law. Newton's second law for a pair of particles subject to an interparticle force, okay, that depends on the relative distance between the particles. Yeah, I'm looking at something fairly concrete. They have two particles, say, I mean, they could have different masses. I've just taken them to be equally massive. And we have some origin, and this is R1, and that is R2. You observe them from two different frames, the unprimed and the prime frame. Now, the distance between the two particles is given by the magnitude of the vector R1 minus R2. Yeah, I mean, this is just a specific example. The force could depend not just on the distance, it may depend on the actual vector R1 minus R2. That too is fine. But let us just consider this as an example. So Newton's equations for the two particles in the original frame, the unprimed frame, are these two: m r1 double dot equal to the force due to 2 on 1, which then depends only on the distance, modulus of r1 minus r2. Similarly, you have the equation of motion for the second particle, and that is m r2 double dot is equal to f1 on 2. Okay, this is the force of the first particle on the second. That again is assumed to depend only on the distance between the two particles. Okay. Now, this is quite common. The force of gravity between two particles or the electric force between two particles depends only on the distance between the two particles. So this is a fairly good assumption for many practically important situations. Now, notice that r prime is equal to r minus ut, and therefore r1 minus r2, when written in the primed frame, becomes r1 plus ut. So here you have r is equal to r prime plus ut in general. So for the first particle, it is r1 prime plus ut, and for the second particle is r2 prime plus ut, of course, subtracted. And you notice that the ut terms cancel out, and so the displacement between the two particles is the same when referred to either frame. R1 minus R2 is the same as R1 prime minus R2 prime. And therefore, if the force depends only on the distance displacement between the two particles or on the magnitude thereof, then the equations of motion will take exactly the same form in the two frames. Yeah, with in the primed frame, you would have exactly the same equation. I can write it here: m r1 prime double dot, because r1 prime double dot and r1 double dot are one and the same, which we discussed earlier, will be given by the same force, F2 on 1 of modulus R1 prime minus R2 prime. Yeah, and the same equation for R2 with all unprimed variables replaced by primes. Okay. So to say it differently, the force that one particle exerts on another does not depend on the frame in which you consider this force. The amount of that force, the direction, its magnitude are one and the same in both frames. And that is what ensures that Newton's equation is exactly the same in both frames. Furthermore, we can also, okay, so let me just conclude that statement. We notice that the velocity u, the relative velocity between the frames, cancels out from the difference in position vectors. Yeah. And thus, the relative velocity between the frames u makes no appearance in the equation of motion in the prime frame. All right, that's gone. And therefore, Galileo's principle can be accommodated here. There is no way from studying this equation of motion that you could have told that this frame is moving at velocity u relative to the S frame. Now, this is not special only to forces that depend on relative displacements. It is also valid for forces that depend on relative velocities. And I think this is along the lines of what was mentioned last time also, or a question was raised last time. So this relative velocity u also cancels out, the frame boost velocity cancels out from the difference in velocity vectors as well. R1 dot minus R2 dot is the same as R1 prime dot minus R2 prime dot. Yeah, if I take the derivative of this equation, I'll get R1 prime dot, R prime dot is equal to R dot minus U. And that is for 1. And R2 prime dot is equal to R2 prime minus U. So taking the difference in velocities, R1 dot prime minus R2 dot prime is the same as R1 prime minus R2 prime. The U cancels out. So the same conclusion applies also to interparticle forces that depend on velocities. And that includes friction. We were saying last time that friction is a force that typically does depend on the velocity of your body relative to the other body. And so let me say this in a positive way. So practically speaking, projectiles move in exactly the same way when observed in two frames in uniform relative motion. And in doing so, we ignore possible variations in external gravitational acceleration. Yeah, so that is an external force. We are ignoring those changes. And second, that a brick sliding on a plank subject to friction displays exactly the same dynamics, irrespective of whether you experiment with that brick and plank below the deck of a docked ship at rest, or a uniformly moving ship. Okay, so any question about these ideas? Okay, so now to clarify further, I want to say what is not true. And that is equally important. So far, we have been talking about interparticle forces within that lab on the ship. Yeah. On the other hand, Newton's second law for a particle subject to an external force. So that is what this equation refers to. Mr double dot is equal to F of R. This one could refer to as just a single particle subject to an external force. This external force could be the gravitational field, the force due to the gravitational field of the Earth. So that is something external to the ship and the room in the ship. This equation of motion is not the same in the two frames. I mean, we did this calculation last time, but my discussion was not proper. So let me do it properly this time. if you rewrite this equation in the primed frame, the acceleration term is unchanged. Mr double dot becomes Mr prime double dot. But the formula for the force becomes different. It becomes F of R. R has to be replaced by R prime plus ut. Okay? So this is the equation of motion in the primed frame. Yeah. And sadly, it is not the same as the equation of motion in the original frame. In particular, the frame velocity u appears in the equation. So the appearance of u in this primed frame equation of motion would mean that one could find out which frame corresponds to the moving ship and which to the docked ship. And to make this very concrete, let us suppose you have a ship that is moving. It is moving on the surface of the earth, and in different places of the earth, there is slightly different accelerations due to gravity, which is now an external force. And you could use that variation of acceleration due to gravity to detect the motion of the ship, even if the ship was moving uniformly. Okay. So just to say that once again, for instance, variation in the acceleration due to gravity at different locations could be used to determine that the experiment was performed in a moving ship rather than on a ship that is at a fixed location on the shore, in the dock. Yeah. Now, this does not violate Galileo's principle of relativity, since Galileo's principle of relativity is not concerned with external forces, not concerned with forces external to the ship and the room on the ship. It is only concerned with the interparticle forces, interbody forces on the ship. So I hope this clarifies some of these things. Any question about this?
Okay, sir. So if there were two, sir, there were two places where in one place the acceleration of gravity was higher, and so you throw a ball, and if it's falling faster, then you know that the ship has moved.
Yes, yeah. I mean, when the ship goes there, you will find that that is the case. And the ship that doesn't move will never observe such a thing at all. Yes.
Okay, bro.
Yeah. Okay. So finally, let me, any other question? Okay. So now going back to something that Ripunjay and Shubham were discussing, let us just briefly indicate why Newton's second law for a particle cannot involve just the velocity. Okay, so suppose Newton's second law did not say mr double dot is equal to force, but rather it said something like a nu r dot equal to g. Notice I am using some other symbol. Instead of mass, I am calling it nu because the dimensions are different, and instead of f, I am calling it g. So this is some variant of Newton's law that we have proposed, and we ask whether it is consistent with the principle of Galilean relativity. Okay, so the difference is that it only involves velocity of the particle and not the acceleration of the particle. Nu is some constant. Then, so suppose this is the equation of motion in the unprimed frame, in the frame of the ship that is anchored in the harbor. Then in a frame that is moving at velocity u, the equation for a free particle would take the form, so you have to do the transformation, replace r by r prime plus ut, then take the derivative. So r dot will become r prime dot plus ut. So let's consider a free particle for simplicity. So the equation for a free particle in the original frame was nu r dot equal to 0 in this new version of Newton's law. And in the primed frame, it is nu times r prime dot plus u equal to 0. Okay. So these two equations are not identical. In particular, the equation in the primed frame involves the velocity of the primed frame relative to the unprimed frame. So the appearance of u on the left of this equation implies that it does not have the same form as the equation nu r dot equal to 0 in S. So in principle, that would allow us to determine the velocity u of the frame S, of the frame S prime relative to S, and thereby tell the frames apart. And Galileo says this is not possible. You cannot, by the study of motion of free particles in particular, to tell whether you are in the ship at the harbor or uniformly moving out at sea. Okay, so that is why we cannot have a first order equation of motion. We need at least a second order equation of motion. So relating the force to the second derivative of position as opposed to, say, the third derivative and so on is at this stage the simplest way of incorporating Galileo's principle. All right. Yeah. And this is sometimes called the principle of parsimony or the principle of or Occam's razor, which simply says that when you have options of I mean a second order, a third order, and fourth order equation, all of which satisfy Galileo's principle, one at least begins by considering the simplest version option as the candidate law. That of course has to be checked. Yeah. So Ripunjai's question was whether one could have some analog of Galileo's principle, but for accelerated motion, and thereby somehow constrain these higher derivatives. And that is a question worth thinking about. Yeah. But in the same context, one must also say that fortunately, experiments and observations confirm that Newton's second law, I mean, as stated, namely mr double dot is equal to force, accurately describes both the terrestrial, that is projectile motion and things like that, and celestial mechanical phenomena, yeah, motion of tennis balls, planets, etc., planetary probes, and so on. So there is no need to include higher derivatives of time with respect to time in Newton's second law, although they would not violate Galileo's principle. Yeah, I hope this is understandable. Please let me know if you have any questions at this stage.
Sir, like another thing. So you said about that principle, right, in which we take the simplest way of defining things. That principle has been applied twice in this aspect. First in choosing the second derivative, and second in choosing it that it is going to depend on one term, like d2r by dt square, right? Because it could have been higher derivative, as Shubham was saying. So it has been applied twice. We have chosen the simplest form of equation and the smallest degree, right?
Yeah. Okay. Now, yes, we have chosen the lowest degree, lowest order. I should use the word order. It could be third order equation or fourth order. They would all satisfy Galileo's principle. We eliminate all of those by the principle of parsimony, Occam's razor. We choose second order equation. Now, you are saying something slightly more. You are saying among second order terms, there are many possibilities. Is that what you're saying?
No, sir. I'm saying we can have like we can have mr square plus say kr cube, like kr triple dot, right? Mr double dot plus kr triple dot. So over here also we say that only we need the first term.
Okay.
And not the second term.
Okay. So look, okay, I think you had, if I understand your question right, there is something to this. See, there is an even more basic principle before Galileo's principle, and I don't know whom to attribute this to, which is that the behavior of projectiles doesn't depend on where you study them. Whether I do it in Chennai or in Kolkata, in the same conditions, they behave in the same way. And it also doesn't depend on when I do it. Do I do the experiment today or day after tomorrow, I am able to reproduce the same results. So this is a principle of homogeneity in space and homogeneity in time. So the equations of motion should also incorporate this idea. I have not mentioned this carefully enough. And if you want that to be the case, the equation of motion cannot depend explicitly on the time at which you did the experiment or the location where you did the experiment. And I think that can be used to eliminate some of these additional terms you are speaking about.
So like this answers Shubham's question automatically, right?
Now I am a little confused about what his question is. But yeah, yes, I think this does address some of that. Yes. I'm sorry. There are at least 3 principles that are gone in here: the homogeneity in space, the homogeneity in time, that is, as well as Galilean relativity principle, in order to motivate Newton's second law. I mean, in particular, why there is not a term in Newton's law that involves simply R itself. Yeah, some new R plus mr double dot. Yeah, why that is not okay. Is any question about that? So let me just mention here that there is another important thing, that the laws of physics. Okay, this is a bit too strong a statement. Let me no, at least at this stage, the laws of mechanics are the same irrespective of the location of the experiment and the time at which it is performed. Okay, so this is called homogeneity in space and time. So when I say laws of physics, I should actually have said that it is observed that physical phenomena or results of experiments are reproducible when performed in another location under same conditions, or at a different time, again under same conditions. and that eliminates certain other terms from Newton's second law, like explicit dependence on the location of the particle. Yeah, so what I mean is an equation of the sort nu r plus mr double dot is equal to force. Suppose this was Newton's law, would violate the homogeneity of space because the location of the particle sort of appears explicitly in the equation. And if you transform to a new frame that is translated, the equation would read nu r plus a. Yeah, you simply translate the frame by a constant vector a. Yeah, suppose you do that, then the equation would read something of this sort, and it would not have the same form. Of course, this will not affect the acceleration term. It will not also affect relative force terms. R1 minus R2 type terms will again not be affected by such displacements. But if there is a term in the equation of motion involving the absolute location of a particle, then it would violate the idea that you get the same result doing it in Chennai or in Jharkhand. So, so such terms are again disallowed. Any question about this? So the appearance of this vector A violates homogeneity in space. Yeah, sometimes this is also called space translation invariance of the laws of mechanics. Yeah, the laws of mechanics must respect invariance under space translations. They must respect invariance under time translations. They must respect invariance under transformation to frames moving at uniform speed relative to each other. Okay, so these are the requirements based on our observations of how nature behaves.
Sir?
Yes.
So this makes sense to me. Like,
yes.
Yes, sir.
Yeah.
This makes sense to me in the sense that, yeah, the laws should not change when we translate in space. But I'm not able to properly reconcile this with the idea that a force can depend on space, on position. So if one has a force.
Oh, please. Yeah, this is a very, very important thing. When we talk about forces, we have to be very clear. Is this an external force? Is it an interparticle force? The whole issue concerns only that. Force can depend on location, definitely. But I think you are thinking of a different kind of force. You're thinking of gravitational force on the earth or something like that. And no doubt, the gravitational force in the Himalayas is different from the gravitational force in Chennai. And therefore, the experiment performed in the Himalayas and here will not have the same result. We do accept that.
Okay. So an concerning only forces like
interparticle forces. Yes, right. Exactly. Interparticle forces.
Right. So if the experiment does not contain any external forces, if we're not so internal forces should not depend on location. Is what this is saying.
Exactly. Yeah.
Okay.
So that is in particular what is being asserted here.
Okay.
Yeah.
That makes sense, sir.
Yeah.
Sir, I had one more question. This was about one of the previous points regarding mu times r dot as a potential equation for Newton's first law.
Yes.
I just wanted to confirm my understanding of that. So
yes.
Suppose that was indeed the equation. We performed it on the shore and we performed it on a boat which is either moving or not moving. And by doing that, we would see that these values don't match. If we measured it, they would not match. And so we would know that there is relative motion, which we should not be able to know by Galileo's principle.
Exactly. Yeah, exactly. Okay. Yeah. Trajectories would be different. The time taken for certain events will be different. And that way you will infer that this particular boat is moving and that one is not moving. You are right. Your statement is correct.
Okay, sir. Yeah. Thank you, sir.
Yeah. Okay. Any other questions? Okay. If not, let me proceed to the next topic. The remaining few minutes. And this concerns a linear superposition of forces. This is also an important principle. So suppose a particle is acted upon by two forces, F1 and F2. Then according to the principle of superposition of forces, the total force on the particle or the resultant of the two forces is the vector sum F equal to F1 plus F2. So, I mean, this is, of course, I think familiar to many of you, but it is important to state it because without that, we cannot work with multiple forces. In fact, it is very useful. The superposition principle is very useful. It allows us to separately determine individual forces on a body, which may have distinct physical origins. Yeah, there may be gravitational forces present, frictional force, electric force, etc. We determine each one through some dedicated procedure, and then you add them up to find the total force. So superposition principle allows you to sort of separate out these things. I am not saying that the solution to the equation of motion with all forces present is the sum of the solutions of the individual equations. That is not being said at all. That is definitely not true. all that is being said is that the total force on a body is the vector sum of whatever individual forces are present.
Sir?
Yes.
Sir, can you once again repeat what you said is not true?
Okay, okay, that is very important thing. We are not saying, okay, so let me write it here. Superposition principle does not say that trajectory or solution x of t, yeah, is the sum of solutions to m x double dot is equal to f1 and m x double dot equal to f2. Yeah. Suppose there are two forces acting on a particle, f1 and f2. You solve the equation of motion with only f1 present or only f2 present. You get some solutions, and you propose that the true solution when both forces are present is, okay, let me call this x1 and x2, is x1 plus x2. Okay, suppose you make this proposal. This is emphatically false. Okay, the solution of the equation of motion is not the sum of solutions of the individual force equations. Okay. This is what is not true. And the reason for that generally is that the forces themselves may depend in a non-linear fashion on the position and velocity. Okay. So because of those non-linearities, you cannot simply take solutions of individual force equations and add them up and get the solution of the when both forces are present. So Shubham, is that clear?
Yes, sir. And sir, one more thing.
Yeah.
Like this linear principle of linear superposition. I mean, is this
of
the
forces?
reason why?
Let me be linear
okay.
superposition of forces, not of solutions.
Yes, sir. Yes, sir.
Yeah.
I mean,
yeah.
Linear superposition forces. Is this the reason why we can consider force as a vector? I mean,
yes. So I think we need to. Yeah. So I mean, in a casual way of saying it, we are using the vector nature of forces to formulate the principle of superposition. Yeah, but I think that is to put the mathematics before the physics. No. The physics is saying that the resultant force on a body is the sum of those forces, and therefore,
yes, sir.
I'm
you
model about that object as a vector, and you postulate that vectors must be addable. Yeah. So okay. I don't want to make a big deal of this, but yeah.
Yes, sir. I was pointing out that only. I mean, this position is this principle is why we can consider it as a vector.
Okay, you put it very well. It is this principle that allows you to consider force as a vector, as an element of a vector space. Indeed, you are quite right. Yeah. Any question about this superposition principle? Yeah, you put it very, very aptly. So I certainly agree with you. Okay, so okay, so I think I am out of time. So rather than rush through the next point, let me hold off on that. If there is any further question on this linear superposition principle, please do ask. Otherwise, we will halt here.
So on the last question, like
yes.
Why is force a vector? On that, like when I thought of it in this way. We see an interaction happening in the universe and we try to quantify it. So to quantify it, we see how am I observing it? I'm observing it in terms of rate of change of momentum, say. So that becomes my expression. Now rate of change of momentum is nothing but like you have your position, like you have your displacement vector, and that has been multiplied with certain scalars like time, mass, and other things. So because displacement was being added in a particular way because of its definition, that initial minus final, so final and initial will always be cancelled. So force automatically becomes a vector because I have defined it to be a vector, and from there I can say that okay, superposition principle will be true, because I decompose the force in two ways because I defined it in that way.
Okay, I agree with you. See, all right. So I think I mean, both of you are correct in your own ways. It is true that for the consistency of this equation, and since f is being equated to the acceleration, the very fact that the acceleration itself was a vector, which is second derivative or first derivative of second derivative position vector and first derivative of the velocity vector. For consistency, the force itself has to be a vector. Am I right? That is what you're saying, in effect?
Yes, sir. Yes, sir. And acceleration, velocity were vector because displacement was vector, and displacement was vector because it is defined as initial and final thing.
Correct.
So
Correct. So yes. So that already tells you that the force has to be a vector, and now the superposition principle of forces is then to be expected. Yeah. But there is no harm in checking whether it is actually true. Yeah. So okay. So you could, in other words, you are saying that stating the superposition principle is somewhat redundant. One might have already expected it from the laws of second. Yeah. So your point is well taken. Now I just want to yes, I appreciate your suggestion, and there is a point to that. Yeah. Well, one needs to be a little bit careful about these things sometimes, and a little bit of redundancy is not always a bad thing. Just to and it is, yeah, but no, your point is well taken. I just want to mention that Newton actually, before writing the Principles of Natural Philosophy, Mathematical Principles of Natural Philosophy's book, he had already written another piece of work on mechanics where he had not 3 laws but I think 6 laws or so, and then he was able to eliminate some of those or derive them as consequences of others, and distill them to 3. So this does happen over time, and so that is why the superposition principle is not mentioned as one of the laws of Newton. I have highlighted it here, but you are right. It for consistency, it already the force does need to behave as a vector. Yeah.
And also,
and just one thing, I think, okay, perhaps it's also a question of one's viewpoint somewhat, or I mean, the foundations of a subject are not entirely clear when it is being formulated, and logic is a rather funny subject. So sometimes, at least physicists sometimes tend to are okay sometimes with the over specifying things. At least it may be that some of these assumptions can be removed, or yeah, but we sometimes just make it explicit, and Newton himself proceeded in this manner. Newton had some version of relativity principle also built into his fourth law. Newton's fourth law is about relativity, but then he discovered that it is actually inbuilt in the second law. It is incorporated there, and then he cast it out in his second book. Yeah. Yeah. So some okay. Your point is very well taken, Ripunjay. Yes.
So what I wanted to ask, what is the name of the first book? I would like to have
okay, I have to look that up. It is some long name in Latin, so I will try to find it and tell you. It was a couple of years or something before. Yeah.
Philosophy Naturalis Principia Mathematica, something like that.
No, that is the Principles of Mathematical Principle of Natural Philosophy. That is the Principia. That is his
second.
Yeah. So that is, yeah. But before that, he had already formulated many things, and it was written down. Perhaps not published in the way that the second book was published. So, but yeah, I will try to find that out for you.
Thank you, sir.
I think he had 6 laws, but I mean, I don't remember very clearly. But I very clearly remember that Principle of Relativity was his 4th law in the previous version. Okay. Yeah, I think also it's also somewhat engineers like to overcompensate for things. Yeah, we don't build a bridge that will just about manage. We over engineer any bridge we want to build. So just to make sure that if the wind gets stronger than we expect that day, it will not fall down. But no, you are right. Some of these some of these principles that I have just said is actually a consequence of the existing one, or at least for consistency must already hold. You are quite right. The question of what is the most economical way of stating the principles is a question of partly of taste and logic. Yeah. Okay. Any other question?
Sir, overcompensation is also good because if the teacher proves everything, then the assignment becomes easier.
Okay. All right. Yes. Okay. Perhaps on that note, then we will make it easy to have lunch now, unless there are any more urgent questions.
So in the 4th problem of homework, do we need to find the solutions of the equation or something like that?
Wait a minute. So in the 4th problem, no, we are not asked to find the. Yeah, no. We are only asked to formulate the equations of motion in matrix notation and to find the powers of that matrix A. Yeah. So that is the question being posed.
Yes. Thank you, sir.
All right. Okay. Any other questions right now? Otherwise, I thank you for your attention, and we shall halt here and meet on Thursday. Please finish your assignment in good time. Please don't wait till the last minute.
So what about mid-sems?
I will let you know about that. Right now, please submit your assignment.
So one more thing, so these notes that you have, these notes are complete, right? So can you upload all of it, like the entire thing, not just the part we have covered, the entire thing?
I mean, as we go, they will be augmented. And see, what happens is that you ask questions. For instance, I had not discussed the homogeneity of space and time. Now that has been discussed. And since somebody asked me to include that, I will include that in the notes and update them and provide them. So I hesitate to give the notes before I have already, before the discussion in the class, because to be honest, they are not complete. So I mean, they are in the process of completion. So I'm not in a position to provide them in advance. I hope you will patiently wait for the class.
Okay, sir.
Okay.
So what are we going to cover in the present course of classical mechanics one?
Okay, the outline of topics is given on the course web page. So that gives a rough idea. Yeah.
Yes. Yeah, thank you.
Okay. All right. So thank you very much. I will stop this lecture now and have a good afternoon.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Yes.
Thank you, sir.
Yeah.
Thank you, Professor.
Thank you. You're welcome.